Okay, my dear students, welcome to you this new class. In the last two classes, we discussed about the linear transformations, definition of a linear transformation, and also discuss about the some various types of examples. I take a different types of example from different types of vector spaces, and so the other thing you have to understand about the how to we have to check the any map which is a linear or not. In this class, we have to discuss some properties of a linear transformations, and in this properties of a linear transformation, we have to use all the basic properties of a vector space as it is. So let's begin with this first property. If we have a V and W be vector spaces and U and V be as vectors in V, and we have a T from V to be a linear transformation. Then we have a T of 0 of V is equal to W. So this means suppose we have a like this, we have a V and we have a like this is equal to W, and this is map is equal to you have a 0 of a V, this is map is equal to you have a 0 of a W, V, and we have a mapping T is equal to this. So we have a this is the element of a T of 0 of a V is the same as this. Every map of a this T always map to the 0 of a V. Okay, let's we use the basic properties of a vector space. We know that there is a two types of properties of vector space. We have a 0 of V is always giving a 0 of a V, and alpha of 0 is also giving you a 0 of a V if V is the element of a V, and then alpha is the element of a R we have it if V is a vector space. Okay, so now we starting from this is equal to 0 of a V, and this is can be 0 of V can be written in the form of a 0 of a V vector by this property, and now we have a take a T of 0 of a V can be written as T of 0 into V. And now because our linear transformation is giving us a linear, so by the linearity condition this can be written as a T into V, and this is by T is uh, by T is linear transformation, by T is linear transformation. And now because the elements of this is equal to you have a V types, and the element of this time is also is always is the TV types, and because W is a subspace is there, if W is a subspace is there, then T of V also satisfy all the properties of a vector space. Like this you have a alpha 0 times of a any W is equal to you have a 0 of W, and W means we have a W is the we take a W is nothing but is equal to T of V types elements are here. So this means by this property we can just say that by this property 0 of W, because if W is any element of a some W is equal to 0 of a W for all W is the element of a W, and because this W is the elements of this elements is the 0 into T of V types, then this is equal to 0 of a W. So this is nothing but equal to, again by this property we can say that this is equal to T of W. So in this case we can say that T of 0 of a V can be written in the form of a T of 0 of a W. So by this property can be hold trivially this thing. So we can just take a 0 vector right in this form. So this way we just say that into this form. T is linear, and then we have to using the condition of a this thing. So now T of you have a given is T of minus U is equal to minus of a U. You know that again we have to just say that minus 1 into U is equal to minus U form of this thing, and then we have to just using this technique here. So U minus U can be written as a minus 1 into U, and if we have a T of minus U can be written as a T of minus 1 into U, and you know that again T is a linear, this can be written as a minus 1 times U, and because of a T is linear, and so this means you can just say that by the linearity, since sorry, I'm sorry, this is nothing but equal to T of U, okay, minus 1 into T of U. Okay, so this can be written as minus 1 and minus 1 into U by the linearity condition, because minus 1 into 2 by T is a linear, And again this can be written in the form of, we can just say that in the minus of, this is, sorry, this is, I have a misprinting here. This should be a minus times t of u. This is not, this is correct. Correct word is not is a u, this is a this t is missing, this is a t times of a u. So this means we can say that t of minus u is equal to minus times of a t of u. So this complete the proof of a this. This is clearly you have to correct it. This is the correct word is this, minus tu is equal to minus times of a tu, not u. Okay, so this means this we can say that this complete the proof of the second part, and then we have to just say that minus t of minus u, again this is equal to t of u. Okay, so now we have to prove this t of u minus v is equal to t of this thing. So we can just say that u minus v can be written as a u plus minus v, and then t of u minus v can be written as a t of u plus minus v, and then you know that the t is a linear, this can be written as a t of u plus t of minus v, and again we just now prove that t of minus u is equal to minus times t of a u. This can be written as a t of u minus t of v. This complete the proof of a this part also. So this is very trivial, we can just say that it is proved to this part also. So this way we can just write, and that is equal to t of minus v is equal to minus v by part 2. Now we have alpha and beta are the scalars. So this means you know that we can write this is very trivial case is there. We can start from the left hand side, t of u plus beta of a v, because t is a linear, we can say that alpha u plus t of beta u, and then again by the linearity of a t we can write t of u plus beta times, we can just say that we can write in the form of a t of v, and this is clearly we can write into this form where alpha and beta are the scalar. This is a very trivial case, we can just set into this form, discuss in this form. So this means this is, and now you see what is the important of this property. The important of this property is this, we have to initially show that u plus v is equal to t of u plus t of v, separately two conditions, alpha u is equal to alpha times t of u. If we combining these two properties, we are getting this. If we take a for example we take a beta is equal to 1, so we have a t of alpha u plus sorry v, and then this can be written as alpha times t of u plus t of v. So if we have to adding these two, so we just can say that either we have to check these two conditions for a vector space map is a linear, or we have to check is this is a linearity, and also check this one. If we take a t of alpha u plus v is equal to alpha times t of u plus t of v, for any one of them these three properties we can just check and then verify that satisfy this condition text is a linear or not. This is the very trivial and basic properties of a linear transformation. Okay, so this way we can just say that. Now this result is very important proposition. In this proposition we just take a v and w be two vector spaces, and t from v to w a linear transformation, and we have a v1 v2 vn be a vectors in a vector space v, and we choose any arbitrary vector v can be written as a finite linear combination of the elements of this v. So if alpha beta is scalar, then t of v can be written in the form of also this. So that means clearly we can say that if we have a v is the element of a v, and this v can be written as a finite linear combination of the element of this alpha 1 v1 plus so on alpha n and vn, then tv can be written also as a linear combination, because what we have to do like this, we have this is v, and this is we have a w, and the element of this is equal to we have any v1 and v2 v2. So these are the elements of vector. So if we say basis form this means we can write in the form of this any arbitrary element v belongs to this can be written in the finite linear combination of these vector. And if we have also here the element of we have a t of v1 T of V2 images of this is here. So by the map of this images are here. So we can say that if we have this can be written in the form of a final linear combination of the elements of a V1, V2, Vn. Then T of V can be written as a final linear combination of the elements of a T of V1 plus and T of V2 and so on. We prove this result by using the very basic mathematics, and that the mathematics is called is a we can say that is a mathematical induction. So we can start with the mathematical induction. So we take this if n is equal to 1, then in the n is equal to 1, this is trivial case. Why the trivial case? Because we have a map is from V to W is we have a giving is a linear map. If it's linear, then we have a can say that T of U plus V is equal to T of U plus T of V, and T of alpha U is equal to alpha times T of U, and for all U V are the element of a V, alpha is the element of a scalar. So by this second property, by the homogeneity, or we can say that the T is under the scalar multiplication. If n is equal to 1, we can say that T of alpha 1 V1 is equal to alpha 1 T of V1 is written clearly by the linearity of a T. Now we assume that this is result for true for n is equal to m, means we have to write this T for alpha 1 V1 plus so on alpha m and Vm is equal to alpha 1 T of V1 plus so on plus ka alpha m T of Vm. Means we have to assuming that this result is true for m is equal to n is equal to m. Now our objective is to prove this result in the case of m n is equal to. Now we try to prove this n is equal to m plus 1. If we successful prove that this is result for true for n is equal to m plus 1, then this is true for each and every member of a for all the set of a v1, v2, vn. Okay. So assume that the result is true for n is equal to m. Then we have to denote this. This is the equation 1. So we have a alpha 1 v1 v2 alpha n is equal to form of a alpha 1 t of v1 and so on. We have to write in the form of a t of alpha m and t of vn. Okay. So now what we did it, we have to required to prove that the result is true for t is equal to m plus 1. So if we write T of for m is equal to 1, so we can add one more terms from here alpha m Vm, then we can write alpha m plus 1 Vm plus 1. So we have to write into this form. Now because T is a linear, so we can write this is the form of a T of alpha 1 V1 plus alpha 2 V2 plus so on. We have a alpha m Vm and plus T of we have a alpha m plus 1 Vm plus 1. Now by this, because the result is true for all n is equal to m, and if n is equal to m, the result is true means n is equal to m means this is hold for T of up to m is equal to in the form of this form, and then we can say that this is equal to so this can be written as you have a alpha 1 T of V1 alpha 2 T of V2 and we have a alpha m T of Vm and we have a T of alpha m plus 1 Vm plus 1. Now again T is a linear map, so this is alpha 1 T of V1 plus alpha 2 T of V2 plus so on alpha m T of Vm plus again the linearity of a T, we can say that scalar times T of V of m plus 1, and then this is nothing but is equal to, we can write T of all the T of alpha 1 V1 plus T of alpha 2 V2 and so on T of alpha m Vm. This satisfy this condition. So we can say that clearly this is m plus 1. So this means the result is true for we have a n is equal to we have a m plus 1, and that means we can say that if the result is true for n is equal to m plus 1, then we can say clearly this is equal to true for each and every member of the and so this means this is equal to 1 by this is this missing. So T alpha m T of Vm is equal to by 1, and then we have a this is nothing but is equal to y1, and then we have a this is alpha m plus 1 T of Vm plus 1, and then hence this is missing terms here. So this means this can be by the linearity of a T here. So m is equal to 1. So mathematical induction we get the we have the required result. So we just this now we have to, based on this result, we have a problem. Suppose we have a determine whether the linear transformation P2P defined by this is a linear or not. We have to prove the first condition is a T of 0 of a V is equal to 0 of a W. Means if T is a linear map, then this is condition should be hold, and if this condition is hold, then we have to just say that T is a map linear. If T is a linear map, this should condition should be must be hold is there. So this means if this map is a T linear, then this should be satisfied. T of 0 is equal to 0 of 0 of a V is equal to 0 of a W. Now what is the zero polynomials? We know that the zero polynomials is nothing but is equal to polynomials of a P2. Zero polynomial of a 0 of a V is nothing but 0 plus you have a 0x plus 0x square, and we have to just take what is the T of 0 polynomial. So you have a 0 plus 0x plus 0x square. This is nothing but equal to T of 0 of a V, and this is defined in the form of a this. We have a constant term is equal to 0 plus 1 plus 0 plus 1x plus you have a 0 plus 1 x square, and then this is nothing but is equal to you have a 1 plus x square, and this is clearly this is not equal to the 0 of a W, and this means we can say that T of 0 V is not equal to 0 of W. So that means if this does not satisfy this required condition of the this thing by the this property, by this property we can say clearly this map defined by T from V to V defined by this is not a linear map. Okay, so now very clearly we have to using this, the zero vector in the zero polynomial means that all the coefficients of A, B, C are 0. So you can write in this form, and then we have to write this. This is clearly is not equal to 0. So T is not a linear transformation because T of 0 is not equal to 0. Why? Because this is a property. We have a linear map. This should be must be hold is there. For this is true for each and every member of a this linear map. So this we can say that the T of 0 0 is not equal to 0 if T is a linear map. So T is not a linear map. That means this is equal to this. Okay, so now we just say we have to discuss some properties of this case, and we have to try to find out by this property of how we can giving a linear transformation. This application of actually this theorem, this previous theorem, we have a by this theorem is very useful because if we have a giving, we can define any linear transformation. If we have a map is T1, V2, V3 given, then we can define a general linear transformation, or we can find any basis of a given element, then we can write V. If we have a V, then TV is in the form of this form. So we have to discuss these types of a property into the next class. I have to discuss, you have a in the end this statement of this result, but because of a due to shortness of a time, I cannot complete the proof of this theorem, this lemma. This lemma simply say that if we have a T and S be a two linear transformation, and we have a V can be written as a span of a V1, V2, Vm, and then T of Vi is equal to S of Vi for each I, then S is T is equal to S. This is simply say that if you have a T of V1 is equal to S of V1, and then we have a T of V2 is equal to S of V2 and so on. T of Vn is equal to S of Vn, and if this is happening for each and I T of Vi is equal to Si, then we can say that these two linear transformation is nothing but they are the same linear transformation there, because V is explained by V1, V2, Vn, because we have to taking these two linear transformation. This is V2W and S is also the from the V2W. So thus this way this transformation we can say into simplify. So that's things very this result is very important. In this case we can just say we have to take T of Vi is equal to S of I. So thus we can just check. Look, let us try to, we have to prove this result, and then we have to stop for the next before the next result. Okay, so we have a proof is this. We have a V belongs to the arbitrary element of a V, then V can be written in the form of a element of a V1, V2, alpha 1, V2, where each alpha I is equal to scalar, and we have a, because T of Vi is equal to S of Phi, we can start from T of Vi can be written into this form. But this previous result is saying that if V can be written in the form of a alpha 1 V1, alpha 2 V2 and so on plus alpha and Vn. If Vn and V2 are the set of vectors, then T of V can be written as alpha 1 T of V1 plus alpha 2 T of V2 plus so on alpha and T of Vn. So we apply this result here. So this can be written in the form of this form, alpha 1 T of V1, alpha 2 T of V2 and so on. We have alpha and T of Vn. Now we have a given T of Vi is equal to S of Vi. So in place of a T of V1, because we have a T of V1 is the same as S of V1, T of V2 is equal to S of V2 and so on. T of Vi is equal to S of Vi. So in place this we can write S of V1, S of V2 and S of Vn. And now because S is again you have a giving is a linear map. If S is a linear, then this can be written in this form, alpha 1 S of V1 can be written as a S times alpha 1 V1. And similarly if you have a alpha times 2 S of V2, this can be written as a S of alpha 2 V2. And then we have to, in the similar fashion, alpha n S of Vn can be written as a S of alpha n Vn. And then because we have a like this alpha S of alpha 1 V1 plus S of alpha 2 V2, by linearity of this can alpha 1 V1 plus alpha 2 V2. In the similar fashion we can just take these two sum and then we take this, and then we can write S is equal to alpha 1 V1, alpha 2 V2 and so on. And then since V is an arbitrary vector, we have to choosing V. So this shows that T is equal to S is equal to V. Okay, so now we complete the proof of this lemma. Base of this lemma we have to discuss into the next class. We have one more very important theorem is saying that when we have a linear transformation T from V to W, then there is a unique T of Ui is equal to some Wi element of this. So the image belongs to the unique. We have to discuss into the next class. So I have to stop this class today at this point, and thank you for your watch. Thank you very much. In the next class, I have to prove the one theorem, and we discuss some problems how to we have a vectors is giving by using this two property. We can generate the general linear transformation. How to write we have some vectors is giving, and by this vectors we can how to write a general linear transformation of a given vector space is there. Okay, thank you very much for this class. We have to meet you again into the next class, and then we discuss some new type of result and some more problems in this thing. Thank you very much for this thing.